Afternoon, guys. We are meeting once again. This is Engineering Science N4. We are trying to recap on our beams. And so as we are recapping on our beam, I think you can see the diagram which I have on the board is clear and visible. So this is a simple diagram that we are having. So I will try to take you through the journey step by step. Beams, they don't change. This is a beam for N4. They are very simple, easy marks which you can get without much stress. Now if you see at our beam, the question says a light uniform beam which is 7 meters long is supported at points B and D. Now, if you see at our diagram, we also have a uniformly distributed load, which is marked by 5 kilonewtons per meter. So our first step, which we need to do before we do anything here, let us fulfill the law of moments, which says downward forces equals to upward forces. So we can add all our forces which are going down. So we have 20 plus 30 plus 30. So, but if we add 20 plus, rather 30 plus 30, we are getting 60 plus 20, which becomes 8. But we have a small problem because we have 5 kilonewtons per meter. We need to change our UDL so that it becomes like the normal concentrated loads or point loads. So how do we do that? There are many ways where we can do it. The simplest thing which you can do so that it becomes easier for you when you're drawing your shear force diagram, you can now see that the UDL is covering a distance from A to point C. So we can do it in proportions where we say the distance from here to this point is 5 meters, but from this portion C to D, the diagram shows that the distance is 1 meter. Therefore, what we need to do here, we can say the 4 meters, which is now the distance from this point to this point, it becomes 4 meters because from here to here it was 5 meters. But this small portion of CD, it is allocated to 1 meter. So if we say 5 times 4 meters, what are we getting there? 5 times 4, we are getting 20. So at a point like this here, in between this point here, in between B and C, we no longer have 5 kilonewtons, we have a point load of 20 kilonewtons. We have a point load here of 20 kilonewtons. Now that point load of 20 kilonewtons, we now have a remainder of 1 meter because the UDL is covering from B to C. So we need to also know the point load between A and B. So A and B, we say 5 times 1 meter. So we now have another point load here of 5 kilonewtons. So once I see that you have broken your diagram into this, it becomes easier for you to get everything right. So we can add our downward forces, which we said is 20 plus 30 plus 30, which we are getting 80 plus 20, it becomes 100 plus 5, which becomes 105 kilonewtons. So in other words, our downward force is 105 kilonewtons, which is to say, for equilibrium, if we add our answer B plus our D, which is our support, it must also give us 105 kilonewtons so that we fulfill the law of moments. Now, the first question here says, calculate the reactions at the supports. Our beam is supported at B and D. So let's calculate the reactions at the support. Let's calculate the reactions at the support. Now, to calculate our reactions at the support, we are going to say reaction at B times the distance between B and D. The distance between B and D is 5 meters. So when we are looking for our point load B, all the components or the forces that we have on top, they rotate to point D. In other words, we are saying clockwise moments equals to anti-clockwise moments. Which points are going to point D clockwise? In other words, we have plus, or rather equal, plus a third times 1. The distance from this point to this point is 1 meter. So this is our clockwise moment equals to anti-clockwise moment. All the forces that are going to the same point B, so we have 30 kilonewtons times to point D, it is 1 meter, plus what we have 20 kilonewtons, so times. Now if you check here, we said 20 kilonewtons, it is cutting 4 meters into what? Into half, which is to say from this point to this point becomes 2 meters. From this point to this point it becomes 2 meters. So from this point already we have 2 meters for 20, so 2 meters plus 1, we've got what? 3. So it's 20 times 3 meters. Plus, let's go to 5 kilonewtons. 5 kilonewtons, once again, it's also cutting that 1 meter into half. So this becomes 0.5. This also becomes 0.5. Remember, we position our UDL at the middle of the covered or the given distance. So from this point to this point, we already say from here to this point, it's how many meters? 5 meters. Plus the 0.5. So we have 5 kilonewtons times 5,5 plus the 20 kilonewtons, which is the last force, 20 kilonewtons times the distance to D, which becomes now 6 meters. Therefore, we solve our diagram with RB times 5. So here we get plus 30 equals 2. We also have here, we also have a 30, yes, and then we have plus 20 times 3, we have 60 plus 5 times 5,5. What do we get? 27.5 plus 20 times 6. We have 120. So let's add everything here. We have 30 plus 60. Or rather, here it's a small mistake. 20 times 3. It gives us. Let me just check. Oh, so otherwise we are fine. So we have 30 plus 60 plus 27.5 plus 120. I'm getting RB times 5 plus 30 equals to 237.5. So it becomes RB times 5 equals 2. So we take this one to this side, becomes minus 30. So we are getting 207.5. We divide here, we divide here. So our reaction at B, we are getting 41.5 kilonewtons. I hope you are following. I hope you are following. I hope we are following. So that's how we get our reaction at B. That's how we get our reaction at B. Now the second concept, let's look at our reaction at point D. Now reaction at point D times, we multiply by the given distance times 5. But just remember, when you are doing N4 engineering science, if you are 100% sure that your reaction at B, the answer is 41.5, there is no need for you to calculate RD using this longer method. If you know that your answer is correct, you can simply say, therefore, D equals to 105 minus 41.5. And then you get your answer. They will give you a full marks for N4. But if you are not certain that your answer is right, there's no problem. You can still calculate it. So let's go through this one once again. Now what we are doing now, because we are looking for D. So when you are looking for D, all the components are rotating to point B. In other words, we are saying anti-clockwise moments equals to clockwise moments. Now let's look at the components that are going to point B anti-clockwise. We have this one, which is 20 times 1, but as well as 5 times 0.5. But 1, 2, 3 forces, they are going to point B clockwise direction. You can see this one comes here clockwise, this one comes here clockwise. Same applies, comes here clockwise. But 5 times 0.5 goes here anti-clockwise. 20 times 1 goes here anti-clockwise. So we say plus 20 times 1 plus 5 times 0.5. These are the clockwise moments. So anti-clockwise moments equals to our clockwise. Which ones are going here clockwise? We have 20 kilonewtons times the distance to this point, which is 2 meters, plus 30 rotating to this point, it becomes 30 kilonewtons times 4, plus 30 rotating to this point, it becomes 30 kilonewtons times 6 meters. So let's solve our diagram. Reaction at D times 5 plus 20 plus 2.5. And then equals to 20 times 2, we have 40, plus 30 times 4, we are having 120, plus 30 times 6, we have 180. So let's add everything here. We have reaction at D times 5 plus we have 22.5 at the 2 equals to 40 plus 120 plus 180. We are getting 340. So therefore reaction at D times 5 equals to 340 minus 22.5. We are getting 317.5. Both sides by 5. Divide both sides by 5. So reaction at D 317.5 divided by 5. I'm getting 63.5 kilonewtons. Now we can prove to achieve whether are we going to get 105. So if we add 41.5 plus 63.5, so we have 41.5 plus 63.5. Indeed, we are getting 105 kilonewtons. In other words, it shows that your diagram is what? In equilibrium. So once your diagram is like this, you're 100% certain that all your calculations are fine. The second step, they want us to draw the shear force diagram. They want us to draw the shear force diagram. Now, to draw the shear force diagram, let me try to, okay, I think I'll just use the similar pen, or I think this one can work. It's fine, let me use the same pen. Now, let's go to this point. We are drawing our shear force diagram. We are now drawing our shear force diagram. We are drawing our shear force diagram. So I'm just putting these dotted lines or these broken lines on every point where there is a point load. At 20, we have a point load. At B, we have a point load. At C, we have a point load. At D, we have a point load. At E, we have a point load. But if you look in between A and B, we don't have a point load. We have an imaginary 5 kilonewtons, which was as a result of a UDL. Same applies to B and C. Between these 2 points, A, B, and B, C, you see the difference that we are going to have as we draw our shear force diagram. So we can draw our straight line. This column, it's for the positive. When your answer is negative, it falls below this one. Now, when we draw a shear force diagram, we draw a shear force diagram from the left to the right. Now, at point A, let us look at the behavior of the force acting at A. Where is it going? You can see our force is acting going way downwards. So we draw a line here of 20 kilonewtons. Remember, in N4, we don't draw to scale, we draw analytically. In other words, we are drawing a thinking. Okay, so if I move a smaller distance from this point to a point like this, which I say is 20 kilonewtons, but between A and B, we have a UDL of what? 5 kilonewtons. Don't forget, already here I said any force that is going to fall behind here or on this column, they are negative what? Negative forces. So any force that is falling here is already a negative force. I don't know why my pen is running out. Let me get another pen. Okay, so I managed to get a pen. So when we draw our shear force, we've drawn a line going downward to this point of minus 20 kilonewtons. So minus 20 kilonewtons minus 25. We have, or rather minus 5, minus 20 minus 5. Because here we don't join a straight line because it's an area covered by a UDL. So we slope joining the second force. So we have minus 25 kilonewtons. At this point, this is our B. We have a force going upwards, which is our reaction at B. So we now say minus 25 plus. Why are we saying plus? Our B, it's a force going upwards, so it's a positive force. So plus 41.5, we are getting our answer is 16.5 kilonewtons. Now, at this point where we are between B and C, but we have a UDL of what? Of 20. So we cannot join a straight line because BC is also covered by a UDL. So what do? We slope. So positive 16.5 minus 20. We are getting minus, so I slope up to a point like here. I'm having minus 3.5. At this point where I am, I'm at point C. At point C, I have a force going downwards. So minus 3.5 minus 30, which is this point. So I'm getting minus 33.5. Minus 33.5. Where I am at this point, I need to join the second force. It's a straight line because CD, there's no UDL. So, and the force going upwards is 63.5. So, minus 33.5 plus 63.5. We are getting up to a point like here. You draw a line going upwards. I'm getting 30 kilonewtons. And then we join the last component. So if you check at where we are at E. Now at E, where is the force going? The force is going downwards. So 30 minus 30, it gives us 0. So at this point, when you get a 0, that's where your shear force is supposed to be ending. I hope you are following. The second part, we are going to do the calculations of the bending moments. I hope we are following. I hope we are following. Now, let's go on our bending moments. Now, the question says calculate bending moments at B, C, and D. So we need bending moments at B, C, and D. So we already know that bending moments at B, we can calculate our bending moments at B from the left hand side. But in the exam, you can choose any side which you want. So bending moments at B from the left hand side, we have a minus 20 times the distance from here to here is what? It's minus 20 times 1 is plus minus 5 times 0.5. So I'm getting my bending moments here as minus 22.5 kilonewton meter. So we are calculating our bending moments at B. So what did I do here? We are saying 22 minus 22 times the distance from A to B, which is what? Which is 1. So I said left hand side equals to minus 20 times 1, which is the distance from here to this point. Plus the second force between that area is minus 5 times 0.5. We are getting negative 22.5 kilonewton. So that becomes our bending moments. That becomes our bending moments at B, minus 22.5. Now let's calculate our bending moments at C. If the one bending moments at C, there's no problem, we can do that one. But the easier way, we can use the right hand side. Now, if you calculate bending moments at C from the right hand side, you can start off by your positive. What's our answer for positive? It's positive 63.5 times the distance to C, which is 1 meter, minus. Remember, we are calculating bending moments at C. So we must also say minus. We take all the forces from the side that you are coming from. So minus 30 times 1. So we have taken our 30, rather not times 1, times 2, because from 30 here we are going to point C. So let's get our answer. We have 63.5 minus 30 times 2. I'm getting a 3.5 kilonewtons meter. So that's our bending moments at point B, at point C. That's our bending moments at point C. So BM at point C is 3.5 from the right hand side. Lastly, bending moments at D from the right hand side, which is minus equals to minus 30 kilonewtons times the distance to D, which is 1. So we are getting our answer is minus 30 kilonewton meter. So we are done when it comes to calculations of our bending moments. We are done when it comes to the calculations of our bending moments. Now, the last step, they want us to draw the bending moments diagram. So to draw our bending moments diagram, we come here to this point, our plus and our minus. So if you look at our diagram, bending moments at the peripheries of our diagram, which is our A, and the E is always equals to 0. So our bending moments at A, so it's 0 here, at E is also equals to 0. What did we get as our bending moments? At B we got negative, so we are going to draw it going downwards because our answer is what? Negative. So we have negative 22.5. And then bending moments at C, we got our answer as positive 3.5. So you can come to a point like this where we have positive 3.5 kilonewtons meter. And then our bending moments at D, we have negative 30. So what do? You come downwards. That's our, yes, you come to a point like this. This negative 30 kilonewtons meter. And then from there, what do? You join your diagram. That's how you draw your bending moments diagram. So these are 3 marks in the exam. If you try to follow the steps, if you have got questions, you can also as well, for those who are watching live, you can check, you can put them on the box and then I'll answer them. Thank you so much.